This is project 26 of Hacking with Swift. We're going to make a rolling ball game for your iPad using the accelerometer. You tip your device and the ball rolls in that direction. But you'll also learn about how to use fine-grained contact bitmasks, how to reverse arrays, how to write code that runs in the simulator but not on device, and much more. So hopefully you'll learn lots and have fun at the same time. For more information, see the website hackingwithswift.com. You can buy the videos there in beautiful high resolution or download them as ebooks for just $3 a shot. Very cheap, and your support is hugely appreciated. Thank you so much. It does help me make more videos like this one. You can also find me on Twitter. I am at 2straws. If you have questions, feedback, suggestions, love, hate, who knows what, follow me there. Get in touch. I'd love to hear from you. Okay, let's go. Go ahead and launch Xcode. Choose Create New Project. And choose iOS Application Game. Next, and I'll name mine Project 26 because this is Project 26. Except this time without the caps lock. Caps lock is cruise control for cool, but it does look bad in projects. For devices, choose iPad and press Next. Then Create. So it creates somewhere on your file system. Cool. I'm going to actually lower my deployment target to be iOS 8 because I'm running Xcode 6.2 Beta 3 here, and my current iPad's only 8.11 iOS. So I'll put it down to 8.0, and I'll choose the iPad 2 for my simulator for now. We do need to try on the device later because the accelerometer obviously only exists on actual devices. Your laptop or your iMac does not tilt. But for now, we'll use iPad 2 and then switch to an iPad, a real one, later on. Please disable all orientations except landscape right. Normally you have both landscapes, now it's just landscape right. This is because you'll be tilting the device to turn the ball and make it roll around. And if your whole screen rotates while someone's playing, it's very annoying. Don't do that. Go to the images, X the assets, zap the spaceship, go into the game scene, zap all the code from did move to view, but not the actual thing itself. Again, all of such as began. And please also pull in the files for this project, which you should have got from the website, hackingwithswift.com. Here they are. I'll just grab all those. I might put them to a little folder to make my life a bit cleaner inside Xcode. Put them in a folder called content, like that. Boom, and then put that folder into Xcode like that. And yes, copy items if needed. Fantastic. Okay, in this project, we're going to use accelerometer, which is not supported in the iOS simulator. We're going to write some hacks. We're going to put in some hacks so it works in the simulator or on devices. And we'll come to that as you hit them. First things first, we're going to tackle a method called load level, and it's responsible for loading a level file from disk and creating sprite kit nodes on screen. Now this is, you can do this in a few different ways. I'm going to choose the most basic programmatic way of doing it to do the work ourselves rather than have our Xcode try and do it for us. But this method is complicated, and it's simply it's not because it's doing a lot of work. It's merely that there is a lot of things to handle, what kind of things to load inside the level. And I want to show you what level looks like first. So open up content and look for level1.txt inside level here. That is how we're going to format a level inside our program. And the various things mean X means a wall, a space means a gap the player can roll their ball through, S will mean a star, V will mean a vortex, and F is the finish, where they have to try and get to finish the game. Using this super simple level format makes it very, very easy to edit levels in a very visual way. Just write the letters where you want them to be. And you can do that in, anyone can do that on an iPad or even a Windows machine if you're very unlucky. But it also makes it very easy to load. So we can just say, what letter is that one? Next one, next one, next one, next one. Now the whole thing adds up to exactly the right size. I've made each of my graphics in here. If you look at them, if I open up, say, a block, which is a single square, one of these X's, the @1x of that is 64 by 64. Now that's helpful because the iPad screen is exactly 1024 wide. So if you divide 1024 by 64, you get 16, which means you get 16 walls across the way. And the iPad screen height is 768 points, which means you get 12 blocks high. So this layout is 12 rows by 16 columns, and this exactly matches a full iPad screen for squares. So each one of these matches a 64 by 64 square. So we're going to loop through this thing and read the lines out and draw them onto the screen. To do this, we're going to loop through the array of lines and see what each character is and put the right thing on there. But there are some catches. First up, we're going to use the enumerate function. We used this before. It lets us extract an index and an item as we go. But we need to invert the y-axis. We'll read this one first and say, okay, there's your first row. We can't place it at 0, 0, bottom left, because that's sprite kit's at the bottom, and this is the top row. So actually, we have to invert the array and load bottom first, like that. So we'll read the array backwards, like this, and go up the way to the top, like that. It's not hard to do, and I'll give you a very, very simple structure first, and then we'll fill in the gaps as we go. So in gamescene.swift, make a new method called load level. So we'll do func load level, like that. And what this needs to do is first load the text file. So we'll find out where it is first. So if let level path equals ns_bundle.main_bundle.path for resource, and it is called level 1. The type is just txt, like that, txt. I'll get rid of this right hand bar here so you can see more on my screen. So if we've managed to find the file in the file system, we'll unwrap that into level path, and then if you manage to load the string, we'll say if let level string equals ns_string contents of file used encoding. Remember, you must use used encoding, not just encoding. And I'll use level path use encoding nil, error nil, like that. So we've managed to load the string from the file, from the path. Then we'll just pull out the lines. So we'll say let lines equals level string dot components separated by string, and we'll use \n, i.e. line break. You must cast this, remember, as a string array, like that. And now we're going to loop through in reverse the rows. So we're going to write for row line in enumerate reverse lines. You have seen this one before. That will pull out each item into here, and also it's indexing the array into here. This thing is new. That reverses the array first, so it flips around lines, so it'll read from bottom to top rather than top to bottom. Reverse it first, and then enumerate over it. So we'll load the array in reverse because Xcode counts. SpriteKit counts from bottom to top rather than top to bottom, like someone drawing the level would do. Now we're going to enumerate through each letter in the line. So we'll say for column letter in enumerate line, like that. So enumerating over all the rows and enumerating each letter in each row. So at this point we know our position, because our position is there's our row and there's our column number. All we have to do is multiply them by 64, because each brick in the game world is 64 by 64. So we can say let position equals CG point 64 times column, because column's going left to right, obviously. So that's 64 for the X, and then 64 times row. Now remember, SpriteKit counts centered on things. Actually, I missed that X and Y here. It's required. SpriteKit centers its things as opposed to the bottom left or top left corner. So to make this align neatly with our sizing, you want to add 32, which is half 64, to each of these numbers. Like that. So that positions them correctly on the screen. And now we have to say, well, what letter is this? And based on that, add the right thing. So I'm going to add a load of if-else statements in here that we'll fill in as we go. So if letter equals X, we're going to load a wall. Else if letter is a V, load a vortex, i.e. the thing that kills the player. Else if letter is S, we'll load a star, give them a chance to score some points while they play. Oops. And then else if letter is F, we will load a finish flag I can get to. That's it. And there is room here for you to do else if, else if, else if for other things you want to add later on. Please do make it more interesting. We're going to fill in those comments shortly. And to be honest with you, most of the code is the same. You know, whether it's a wall or a vortex or a start or a finish, the code is nearly all the same. Load an image, position at this position we generated here, give it a physics body, add it to the scene. Now they do vary because of course we want players to collide with some things, we want to be notified of other collisions and so on. But we're going to use 3 bitmasks to make this work. And at this point you need to really understand what these bitmasks do. There are 3 bitmasks: the category bitmask, the contact test bitmask, and the collision bitmask. We have very precise rules for each of these. It's important you understand how they work. First, easy one, category bitmask. This is a number defining the type of object this is for considering collisions. So you can say this is a wall, this is a vortex, this is a star, this is a finished thing, this is the ball, this is whatever, right? It's a category, it's a number, so you don't actually say wall, you say 1 or 4 or 16, whatever it happens to be, that means wall. Next up, collision bitmask. This is a number defining what categories of object, using category bitmask, this thing should collide with in the game. What should it bounce off? And by default, it's everything. Collide with everything and bounce off everything. And finally, contact test bitmask. This is a number defining what categories of object this node should collide with. That should be reported to us. What collisions do we care about? So for example, should a ball, the player, should it bounce off vortexes? No, it shouldn't. It should get sucked into them. So it shouldn't bounce. It should actually be able to overlap vortexes. And it should overlap it. So it shouldn't bounce off it, but it should have the contact test set so we get told, hey, the player got sucked into a vortex. Same for stars. They shouldn't bounce off each other, but they should overlap and collide so we know about them so we can react to them. For walls, yes, the ball and the wall should bounce off each other so the ball can't escape the little maze we'll set for him. They're all different things. It's important to understand exactly what they do. And before we use weird hacks and stuff to cheat, this time we're going to do it properly. We're going to have a bitmask for each thing in our game, and we'll assign them as we go. So this is going to require an enum to do it nicely, because you could put numbers in there, like we did in the last game project. We just put in 1, and that's fine. But you're getting better now. You're learning the right way to do things. So we're going to have an enum with numbers attached to it that lets us use proper collision types. So before your class, we want to say enum collision types is a uint32. There he is. That's the type SpriteKit wants for bitmasks. And this needs to have a few different possible properties. First is a player. And this needs to be 1. It's a number that matches a text string. You can make it 16 or 32 if you want, but it needs to be a number. The numbers are generally powers of 2. So we'll do 1, 2, 4, 8, 16 here. That's the way to do it. Then we'll say wall. Well, a wall can be 2. A star, that can be 4. A vortex equals 8. And the finish area is 16. Like that. So we now have numbers for player, wall, star, vortex, and finish. 1, 2, 4, 8, and 16 respectively. So SpriteKit will compile these down to these numbers here. We refer to them as these text things here. So we get the best of both worlds. SpriteKit's happy and we're happy. We don't have to remember what 4 and 16 are. It's much easier this way. So with that done, we can start replacing the various bits of our code. So when we say load wall, we're going to load a node in here. We'll say let node equals sk sprite node, image named block. Very tedious, slightly ugly, admittedly, wooden block, just like that. Oh, by the way, the graphics in this game, they're pretty ugly. I'm a coder, not an artist. You can find your own art person to do brilliant graphics for you. Sorry. So that loads a block. We want to position it where we said before. So we'll just do equals position, like that. Give them a physics body. I'm going to make it a rectangle because these are just square. So node.physicsBody equals sk physics body, rectangle of size, node.size. Then we're going to put the right category bitmask. This isn't really required at this point for walls, but we'll do it to be nice and clear. Node.physicsBody dot category bitmask equals collision types dot wall dot raw value. That thing is an enum. This thing wants a uint32. That the raw value is what converts wall into the number behind it here, the uint32. So that means find out the wall's number and put it in there directly. So that makes SpriteKit very happy. We also want to make sure that the walls don't move. When a ball collides into them, they don't roll off the screen, they stay where they are because they are walls. So we'll say node.physicsBody.dynamic equals false. Do not move ever. Finally, add child node, like that. Okay, next up, Vortex. Vortexes. It's vortices, but vortices is a bit silly. It's a bit pompous, so I'll say vortexes, quite frankly. Let node equals sk sprite node, image named Vortex. It is very similar to walls, which is helpful. I'm naming it this time, okay, so we can refer to it later. We'll say node.name equals Vortex. We know this is a vortex, we can refer to it later. Node.position equals position. I'm also going to add an action to this because it looks nicer if these vortexes, this graphic here, I'll show it to you. If they sort of spin gently in the game, it looks like an evil sort of black hole thing, or in this case a red hole. So, node.run action. I'm going to use skaction.repeat action forever. Then action.rotate by angle. I'm going to use mpi. It's required to CG float, so you must cast a CG float. So we'll say CG float mpi. Duration 1 is fine. And then parenthesis, 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 like that. Boom. That will make it spin forever by 108 degrees over 1 second. So it just spins nicely, constantly. Then we'll give it a physics body so we can collide with it. We'll say node.physicsBody equals physics body. Circle of radius this time, because it's a circle, these vortices. Vortexes. I'll do node.size.width divided by 2, because it is a radius, not a diameter. Then again, it's not dynamic. It shouldn't move in the thing. It should stay still no matter what. So we'll do dot dynamic equals false. We get collisions, but it won't move around with gravity and such. Like that. Then we're going to carry on and add also its own category bitmask, its own contact test bitmask, and its own collision bitmask. Remember, category bitmask defines what it is. Contact test bitmap defines what it reports collisions for. And collision bitmask is what bounces off it. So I'm going to use node.physicsBody category bitmask equals collision types dot vortex dot raw value. This is a vortex. Now node.physicsBody contact test bitmask. Who should be what things you care about being told about? I collide with, and the answer is collision types dot player dot raw value. And finally, what should bounce off me? I'll do node.physicsBody collision bitmask. The answer is 0. Nothing should. Because a player should roll over vortices happily. It shouldn't, vortexes even, shouldn't bounce off them. And then we'll just do add child node. So that the vortex appears on the screen. So there's slightly more work happening in there thanks to this big long repeat action forever call here for the action to spin it round and round and round. And we're doing actual bitmasks here. We're saying, listen, I am a vortex, I collide with the player, nothing bounces off me. That's what we're saying. The code to load stars and the finish area are basically identical, so it should be the same code for you. So let's do let node equals sk sprite node image named star, and then we'll do node.name is star, not surprisingly. Node.physicsBody equals these things that they're pretty much circular. They're not square, that's for sure. So I'll use a circle body for that as well. Equals sk physicsBody circle of radius node.size.width divided by 2. Then it's not dynamic because otherwise it would roll around, which looks silly. Node.dynamic equals false, like that. Then we're going to set up its bitmasks. So we'll do node.physicsBody.category bitmask equals collision types dot start dot raw value. It is so much easier to copy and paste this, but I'll type it because I'm a masochist. Then we'll use contact test bit mask equals what do you care about being told about that I collide with? That's a very bad way of explaining it. This means when something touches me, what do you care about? Which of the touches do you care about? And the answer is we care about when a player touches a star because we can give them points. So we'll do raw value of player. Then we'll do node physics body dot collision bit mask. Who should collide with me? And the answer is nothing should collide with me because the player should roll over the star and touch it again and have the star disappear. We'll give it position, of course. Node position equals position, like that. So it's positioned to the right position. And then add child node. Fantastic. And that just leaves the finish area. I'm not going to do much with this. This is down to you and your own code and your own time. So I'll do let node, or luri novi, let node equals sk sprite node, image named finish. It's a little finish cup thing to know the end of the level. Node.name equals finish. Then node.physicsBody equals sk physicsBody. I'll do another circle one for this one, see what works best. Node.size.width divided by 2. Node physicsBody dynamic equals false. Node physicsBody category bit mask. What am I? I am a collision types dot finish dot raw value. And then node physicsBody contact test bit mask equals collision types dot player dot raw value, so that we care when the player touches us. And node dot physicsBody dot collision bit mask equals 0. I actually bounce off nothing. Then we'll position it. No position equals position, and then add that child. Oops. Then add that child to our scene. Our child node. Boom. That completes the method. That's everything. It is the same code multiple times with tiny, tiny tweaks. The interesting stuff is this chunk at the top here, or you have to read the lines in reverse and go through each line, each character in the line, and then multiply by 64 to get the right position and so forth. We know that already. Old stuff. To see the fruit of your labor, to see how it actually looks, it is time to just call this somewhere. So in the did_view method, just do load level. Boom. And that loads it in. You can go ahead and look at it straight away. I would suggest before calling load level, you do add a background picture. I've got a nice ugly concrete thing here you can use behind it. Look at that. Yummy. So before we run load level, let's just add a background picture. This is old stuff for you. So let's do let background equals sk sprite node image named background. It's a JPEG, so you must say .jpeg like that. Background position equals CG point with x 512, y 384. Background blend mode equals .replace. Doing this since project 11 now, so you know this already. Add child background. Boom. Look at that. Okay, let's run that back in the simulator and see if that all works. Here we go. That's a lot of typing. Will it work? Oh, fantastic. Look at that. So you can see we're going to start the player somewhere. They're going to roll around, collect all these stars, try and get to the end without touching a single vortex, as many stars as possible, and get to this finish flag at the end. And the vortexes are spinning around nicely. It looks pretty good, actually. That's not bad. So it's a lot of code, and you could easily clean it up into like a load wall method and a load vortex method and so forth to keep load level down, because ideally you don't want too much code in a single method, otherwise it does get very confusing. But for a start, it's very, very good, and of course you can clean it up in your own time all you want to. Now it's time to add work to show the player. Now, like I said, the accelerometer is standard on all iPads, but doesn't come as standard on any Mac. So you can't just tilt your laptop or your iMac to get things to work. So you either test only on devices, which is okay if you must do, or we put in a little hack. Now, we're not writing a book here called Resigning with Swift or Giving Up with Swift. We're going to add a hack. So it means in the simulator, you can use touch. On devices, you can use tilting. So to get started, we're going to add a property for the player. Go to your top of your class and let's add a property. So this thing is called var player is an sk sprite node with implicit unwrap, like that. We'll make a dedicated create player method that loads a sprite, gives it physics and so forth. But it's going to do three other things that are important. First up, we're going to use a new property of physics bodies called allows rotation, we'll give that the value of false, because our balls, if you look at them, where is the ball? Am I being very slow? There we are, player at 2x. They've got this sort of shine effect going on. And if you rotate the shine, if the ball rolls around as it's moving, it kind of ruins the effect. You wouldn't get that on actual shiny balls. So by making it look like it's not rotating, it looks a bit more realistic, only fractionally. My graphics are terrible. Second, we're going to give the ball a linear damping value of 0.5. So there's a lot of friction on its movement. So the game's still hard, but this does make it a bit easier by slowing the ball down naturally. So if you stand still, if you stop rotating or stop tilting, the ball does just slow down by itself. Finally, we're going to combine 3 values together to get the right contact test bit mask. This is important because the way this works is the ball has to collide with the vortex, and the vortex has to collide with the ball in order for the bit mask to work. They both have to have each other in their reference. So the ball has to be able to collide with the stars and the vortexes to be able to work correctly. And of course the finish area too. Alright, let's make the create player method. So we'll do func create player. So first upload the player. So player equals sk sprite node. It's going to do image named player, because it's a ping. We don't need a dot ping on the end. We'll position it at an exact point that matches the top left corner of the game. So at CG point, X is 96, Y 672. That's where I found the best start point to be. By all means, your game, change it what you want to. Then we'll give it physics body. So player.physicsBody equals sk physics body circle of radius. So player.size.width divided by 2. Then turn off rotation. So player physics body allows rotation equals false. Don't spin it round. It looks much better. We'll give it that linear damping to slow it down naturally over time. 0.5. So there's a lot of friction being simulated on that ball. Then we'll give it the bit masks. So we're going to do player.physicsBody.category bit mask equals collision types.player.raw value. I am a player. That's what it's saying so far. Now we combine star and vortex and finish. These are the 3 things that the collisions we really care about. Please tell us when these collisions happen. So that's player.physicsbody.contact test bitmap equals collision types .star .raw value, then a pipe symbol, which means or, combining the 2, or collision types .vortex .raw value, or collision types .finish .raw value. So any one of those 3 things, please tell us when they happen like that. Then we're going to say, in terms of things I bounce off, I just want to bounce off one thing. So player.physicsbody.collision bitmask, please bounce off the walls. So collision types.wall.raw value, like that, and add the player to the game. Right, you want to put this just after the call to load level. This is important. If you put it before the code to load level, then it will actually load the player and then add the level on top of the player, so you won't be able to see the player at all. It simply won't work. So you want to say, after load level, create player. Run the game now, and you'll see the ball in there, and it'll just drop, bonk, down here. It'll do nothing yet. Obviously, it hasn't collided with the star or the vortex, but it just dropped and fell there, which is not what we want, because by default, if the iPad is flat, there should be no movement. You know, only if the player tilts their device should the ball move. So what we're going to do is we're going to say, by default, we want no gravity. So we're going to do physicsworld.gravity equals CG vector dx 0 dx y 0. So no gravity. And then we're going to modify, as the player tilts their iPad, we'll modify the gravity as they tilt it. So they're simulating gravity in their tilt gesture. So if you press play now, the game has kind of got worse in some respects, because if you look at it, the ball just sits there. It's floating in space now, where there literally is no gravity, so why should it fall? Wouldn't make for much of an App Store success, let's put it that way. What we're going to do is we're going to put our hack in now that lets you simulate the experience of tilting the ball using touch, i.e. using your mouse in the simulator. So we're going to use touches began, touches moved, touches ended, and touches cancelled. And we'll hijack them to set or unset a new property called last touch position. Then in the update method, we'll subtract that position from the player's current position and use that to set the world's gravity. This is obviously a hack. If you are happy to test on a device, you don't need this hack. You can literally forward wind. But if you're stuck on a simulator, you're just curious, then please crack on with this hack. So add this property to your scene. var last touch position is a CG point question mark. It may be there, it may not be there. And we're going to use these in touches began, but also touches moved, and touches ended, and touches cancelled. So we want touches moved, we want touches ended, and touches cancelled. And just delete this sort of code holding thing entirely because it's just getting in the way. Brilliant. So touches began, we do the usual little dance we do. We say let touch equals touches dot any object as UI touch. Get me any touch. Find its location. So let location equals touch dot location in node and then self. And we're going to set last touch position to be the location, so we know where it was last touched. For moved, we're going to do exactly the same thing, so just copy and paste the text. So when it's moved, just again find out where it's moved to and update last touch position. In ended, touches ended, we just have to say last touch position equals nil. Get rid of the variable entirely. We don't care where it's moving to anymore. And again, in touches cancelled, like that. And that's all our touch work. Very easy. It does get a little bit trickier inside the update method. We need to unwrap this optional property, calculate the difference between our current touch and the player's position, then use that to change the gravity value of the physics world. So in update, which was here, let's see if we have a value first. So we can say if let current touch equals last touch position, i.e. unwrap that. If there's a value, put it in here. We're going to make a difference of the two, a delta. So we'll do let diff equals CG point. Then X should be current touch dot X minus player dot position dot X, like that. And then for Y, we want to do current touch dot Y minus player dot position dot Y, like that. So that tells us the difference between where we tapped and where the player is right now, and we'll use that to modify the gravity. So I'll say physics world dot gravity equals CG vector, and then dx should be diff dot x. I divide by 100. I find that's the right sort of value for testing. Again, try your own value. Diff dot y divided by 100, and that's it. That's our hack in place for now. Go ahead and run that and see if this is working. Boom, I should be able to tap on here, and there's the ball rolling. Up here, it slows it down correctly and moves it down again. Look at that, beautiful gravity slowing down. Can move around, back off the walls. Still can't touch vortices, or stars. But the game, at least you can see it's rolling around quite nicely. And now comes the actual interesting bit, which is working with the accelerometer. This is done using a framework called Core Motion. And nearly all the work's done by CM Motion Manager. You don't need any special user permissions. You just need to create an instance of the class, tell it to start collecting information, and then you can read from it whenever you want to. And for us, that'll be in the update method. We want to read from it regularly and see what's going on. So we can say update the tilt, update the gravity, and so forth. So go ahead and import Core Motion above SpriteKit. Core Motion, like that. And now we're going to create a motion manager. So we'll go to here and say var motion manager is a CM motion manager, implicit unwrap. And we'll just create it somewhere. So we'll say here in did move to view, motion manager equals CM motion manager. Then motion manager dot start accelerometer updates. Boom, that's it. Remarkably, that's it. All we have to do now is poll this motion manager, read it back inside our update method, and say what's the current tilt data. Now, there's a slight complication here. If you are using the simulator so far, we've got this hack in place, and we want to be able to test on the simulator and test on devices, if possible, without having to keep on deleting and commenting out code. The way of doing this in Swift is doing something called a compiler directive or a compiler instruction. And this instruction, if it evaluates the true, will compile one set of code. Otherwise, it compiles the other set of code. We can literally write code that only gets written into the app when it's being built for the simulator. So when you build for a device, it builds different code, and it won't be in there. The other code will be in there. The nice thing is, any code that evaluates to false, the condition evaluates to false, never gets seen. It literally erases the code, and it never happens existing inside the app. So you can write tons of stuff, a debug, for example, that never ship on actual devices. The directories we care about are this one. We're going to write in here, above update, we're going to say hash if, octothorpe if, usual sort of, what the hell do we call these things? Hash if, if, and we want to write arch I386, like this, with parentheses too, or arch x86 underscore 64, like that. And everything here will only be executed if it's running on an Intel CPU. Specifically, obviously, that is our Macs. Our Macs are all Intel devices. So that code will only exist on devices that are Macs, not iOS devices. We can then say after that, all that code will do hash else. It's usually done to put these things very, very initial of the lines. You can see them at a glance. That's how most coders do it. If otherwise, we'll do the iOS code. So I'll put in here iOS code here. That. At the end, you just write hash end if. So end the statement. So if we're on an Intel Mac, or any Mac, let's face it, run this code. Otherwise, iOS device, run this code, and then back to normal afterwards. That's what it does. So the iOS code, what all we have to do is read out the current accelerometer data from our motion manager and use that to create our physics, our gravity. So if let accelerometer data equals motion manager dot accelerometer data. So if we have some data waiting to be read, you might not, because if the app's just launched, there'll be no data to read yet, which is fine. So you want to unwrap it very carefully. We then modify our gravity, so physicsworld.gravity equals CG vector. Then for dx, I'm using accelerometer. I can't write here for some reason. Let's use dx should be acceler. Doesn't like it at all. I've muffed something up here. What have I done wrong? Did that build? That builds. Oh, it's because it's being clever. Well, I say clever. It's being helpful. This code here only exists in the eyes of Xcode if we're building for an iOS device, not for a Mac. As a result, it wasn't even seeing the code. I have to try again. If let, sorry, I did that already. Physics world dot gravity equals CG vector with dx accelerometer data. There it is now. So code completion works correctly because it's now reading this code correctly. I just changed the build for iOS device, so this code becomes active basically. So it can now read this if let. Accelerometer data dot acceleration dot y. I'm going to multiply it by minus 50 to get the right sort of values. I've tested this a number of times and I find this to be about right. But again, go through it's your code, knock yourself out. And then for x, we want to do so let's play a second. So we'll do acceleration dot x times 50. Now the reason you're thinking, why putting y into x and x into y? It's not a typo. I have not actually screwed this one up. It's supposed to be like that. Remember, the device is rotated. So what you think of x and y is actually the other way around. We're in landscape mode here, so the x and y are not what you think they are. So they're flipped around. And the whole idea of up and down is all, of course, very different now because we're in a rotated device. So it may not be what you think it is, but those are the right numbers to use in this game. That's the accelerometer code done. You can go ahead and test it out at your own time. It was obviously very, very simple. Even I can get that bit of code right. The next thing to do is look at how we can contact but not collide. How we can collect the stars without sort of bouncing off them. So I'm going to switch back to the simulator so we can see how we look so far. Nothing's really changed, of course. We've got our hack will be compiled in now, so we just click to move around. We want it so that when you go over a star, it rolls over it correctly and picks up the star, ideally. So we need to put the challenge element in, basically. Collect points for stars, lose points for going near vortices. Vortexes, bah. Anyway, let's add a score, because every good game wants a score. We'll do var score label is an sk label node, implicit and wrapped. Then var score is an int that is 0 by default with a property observer. This is like so boring for you now, sure. We've done this 1,000 times so far. Then we use a score colon, string interpolation. Oh, very boring. Score, quote like that. So that all works. We're going to put that label in the top left corner of the screen. So somewhere after doing like create player and load level and stuff, we'll say score label equals sk label node. And we'll do font name. Let's use Helvetica. No, chalk duster. You know, it's your app. You can change it later on. It's fine. Score label dot text equals score 0. Then score label dot horizontal alignment mode equals dot left. Then score label dot position equals CG point. Actually, no, let's put it in bottom left corner. That's a bit nicer for, I think. So x16, y16. And then add that to our scene. Very dull. Now, when a collision happens, it's our job to figure out whether it's a player colliding with a star or the star colliding with a player. We've had this problem before. Our solution is quite simple again. Figure out which is which, then call another method. So first, we have to be the contact delegate for the physics world. So somewhere in the code, in did move to view, we want to say physics world dot contact delegate equals self. Then add us as conforming to the protocol. So sk physics contact delegate. There it is. Boom. It's now time to write did begin contact. So we'll down here we'll put in, look at this massive method. Did begin contact. Brilliant. So all we care about is which one was the player, because that's the only thing things can collide with. They all have contact test bitmap player, apart from the player, which has everything else set. So we're going to use in here if contact.bodyA.node is player, then do stuff. Otherwise, if contact.bodyB.node is player, then do something else. So we'll make a method, and this will be called player collided with node, and it'll take the other thing. In our case, it's contact.bodyB.node, and I'll do a force unwrap of that so we know it exists. In this case, it's body A, the opposite of what it is, because if it's A, we pass in B. If it's B, we pass in A. So there are 3 types of collision we care about. First, when the player hits a vortex, they should be penalized somehow. When the player hits a star, they should score a point. And when the player hits a finish area, the next level should be loaded. I'm going to handle the first 2 for you. The third one's down to you. Let's have a look. When the player hits a vortex, first we want to stop the player controlling the ball. Yeah, they've lost now, give up. And we'll do that with a new boolean called game over. Let's just do it now. In fact, it's one queuing up stuff. Let's just add that now. So let's do var game over is false, like that. So I have to update our update method, even to modify our update method. That sounds much better. Modify our update method. So if game over is false, then we can do stuff. Otherwise, we don't do stuff. So we're going to say if not game over, then do all this stuff like this. Boom. Like that. Yeah. That. So that will only be called, this stuff will only be adjusted if game over is not true. Like that. And then we have to stop the ball from being dynamic so it doesn't move anymore. We want to kind of suck it into the vortex as if it's being warped away to another dimension. When that whole thing's finished, we want to remove the ball from the game. Then after all the actions are complete, when I create a new ball so they can re-enable control again, they can start playing again. So we're going to put that together using an SK action sequence, followed by a bit of trailing closure action that will run when the actions have all finished. Then colliding with the star, we'll just remove the star and add it to score. So let's start with Vortex, the easy bit, or the hard bit, sorry. So, func player collided with node. It's a SK node. And then we'll say if the node is a vortex, we are going to first stop the ball from moving around dynamically. So we'll say player.physicsBody, physicsBody, dynamic equals false. Then we're going to set game over to be true. So the player loses control at this point. And we'll take 1 away from the score because they've been naughty. Then we're going to add the actions to simulate being sucked into the vortex, which occupies a few things. Firstly, as a move action. So let move equals skaction dot move to, like that, and we want to specify a whole point, so we'll do node dot position, duration 0.25, i.e. move to whatever we collided with position, i.e. the vortex's position. Then scale, so let scale equals skaction dot scale to, I'll use 0.0001, so tiny. Duration again 0.25. Then we'll remove it, so we'll say let remove equals skaction dot remove from parent. Then let's put that into a sequence. So we'll say let sequence equals skaction dot sequence. It's an array where it moves, then it scales, then it removes, like that. Remove. Like that. And we'll run that on the player. So we'll put player.run action sequence. Then as a trailing closure, unowned self in. This thing needs to call create player again, which will be self.create player, self.create player. Then self.gameover equals false, like that. So when it'll move to the vortex, it'll suck it down, it'll remove it from the scene in a sequence. Then when all that thing finishes, it will create a new player ball and re-enable game over. So disables game over, so the player can start moving again. That's vortex. That's the hard bit. If it's a star, it's easy. Else, if node.name is star, then node.remove from parent. Just remove the star from the game and add 1 to score. So actually plus a score. I did actually write score minus equals 1 here as opposed to minus score. Because originally I was being quite even doing like score -3, but actually that's quite hard. So playtest it and find whatever numbers work for you for adding and subtracting score. Then else if node.name equals finish, this is down to you. You can write that in your own time. And that method actually remarkably finishes the game. It's now down to you to, of course, try and play the whole level without being sucked into a vortex and finish the finish area thing. But I'll try and play it now, and I guarantee I'll die very quickly. I shall prove actually it does work. I can roll over here and you'll see a star. And it's crashed. It doesn't work because I have made a mistake somewhere. What have I done? Cool. I made a dumb mistake. What did I do? Oh, dear me. Oh, good grief. I've made a real schoolboy error here. So if node name is star, if node name equals finish, and I've got if node equals vortex, I'm trying to compare an object against a string, which is really dumb. Don't do that in your code. Don't be like me. Be smart. Play again. I pretend the rest of the code never happened. I'll scroll down again. I'll click down to roll. Touch the star. Boom, it goes away. And here I hit a vortex, so it should move in, scale down, and restart the game. Fantastic. Look at that. Absolutely brilliant. So now I'll try and not be rubbish. Stay away from the vortex and roll around the ball here a little bit. It is actually easier with tilt because it's more natural. Clicking and moving like this is actually quite weird. Oh, almost died then. And try and get that star. Anyway, you can see the game works. Do play it on a device. It's a lot of fun, the device. Physics and motion, combining the iPad's motion accelerometer stuff with physics is just so much fun. It feels really, really real. So give it a try and see what you think. For more information, see the website, hackingwithswift.com. You can buy this video and all the videos in this whole series as high-resolution quality downloads. They look fantastic. Please do buy them. Or alternatively as downloadable ebooks, starting at just $3 a shot. Very, very cheap. Your support is really appreciated because it helps me make more videos like this one. So please have a look and buy something and support my work. You can also find me on Twitter. I am at 2straws. If you have questions, feedback, suggestions, complaints, comments, love, hate, who knows what, follow me there. Get in touch. I'd love to hear from you. If you use my code, I'd love to hear from you. I'd love to, let's interact. Let's be friends. And that's it. The game is now yours to complete. Have a lot of fun.